Please take your seats.
আচ্ছা তাহলে শুরুটা তো একটু দাঁড়াও আমি আচ্ছা 1 মিনিট একটু এবার আমি কি বলবো স্টপ শেয়ার না কি করব
হ্যাঁ
স্টপ শেয়ারিং করব তো তারপর
হ্যাঁ প্রেজেন্টিং হচ্ছে তুমি করো অসুবিধা নেই
দেখা যাচ্ছে
শোনা যাচ্ছে তো
হ্যাঁ
শোনা গেল
শোনা যাচ্ছে
হ্যাঁ
ঠিক আছে
হ্যাঁ হ্যাঁ হ্যাঁ
সময় তাহলে একটা স্ক্রিনে দিয়ে দেবো
হ্যাঁ দিয়ে দাও আমি দেখতে পাই তুমি করো আমি দেখতে পাচ্ছি
চিন্ময় ওই 4 জন ঢুকলে আমাকে একটু বলো
হ্যাঁ হ্যাঁ হ্যাঁ
কিসে বলবে
দেখতে পাই তুমি করো
বাবাকে বলে দিয়েছি
আচ্ছা রত্নাদি
হ্যাঁ হ্যাঁ বলো
তুমি দোলাকে আমি ইউটিউব লিংক পাঠিয়েছি ওটা খুলতে পারো তো আমি ইউটিউবটা চলছে কি দেখো তো মোবাইলে
লিংক পাঠিয়েছি বলছো আমার একটা পেন শুনছো
ভাস্বতী
ইউটিউবটা চলছে কি দেখো তুমি আমি নিয়ে আসো ইউটিউব মোবাইলটা নিয়ে আসো আমি যেতে পারবো না এখান থেকে তোমার ফোনটা তুমি নিয়ে আসো। আমরা জয়েন করো তাড়াতাড়ি কোথায় তো আমি দেখতে পাচ্ছি না তোমাকে সবাই তো আছে তোমাকে দেখতে পাচ্ছি না তো
আমার স্ক্রিনে কি ওই ফ্লায়ারটা দেখতে পাচ্ছো না আমাদেরকে
আসুন
দেখতে
তো
পাচ্ছ
ওই লিংকে তুমি ইউটিউবটা চালাও না দেখো চলছে কিনা তোমাকে লিংক পাঠিয়ে দেবো
এই
আমি
রঘুপতি
হবে না আমার
বলছি যখন গানটা ছিল তখন স্ক্রিনে ফ্লায়ারটা দেখছিলে
হ্যাঁ হ্যাঁ
এখানে হবে না দাঁড়াও নিয়ে যাও তোমাকে
কি বলিস না আমি কিছু বুঝতে পারিনি
বুকিং আছে
স্টপ শেয়ারিং করে দিচ্ছি
হ্যাঁ ঠিক আছে এবার কি হচ্ছে
তাহলে প্রেজেন্ট নাওতে গিয়ে ইওর এন্টায়ার স্ক্রিন
চিন্ময়
হ্যাঁ স্যার
চিন্ময়
বলুন স্যার বলুন শুনতে পাচ্ছি স্যার
বলছি যে কটায় শুরু করবে
হ্যাঁ শুরু করে দিলে হবে এবার শুরু করে দিলে হবে করে দেবো
ওই এখনো আছে তো
মর্নিং এর প্রিন্সিপাল
না 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 টাইমটা মেনটেন করতে হবে তো
হ্যাঁ
টাইম ঠিক লাগবে
স্পিকার আসেনি তো
আমি
মৈনাকদা?
মৈনাকদা আসেনি
না মৈনাককে দেখো মৈনাক এসছে
না মৈনাকদা আসেনি বললো তো ঢুকে পড়বে
মুকুট
মুকুটদা মুকুটদা ঢুকবে 6টার সময়
ম্যাডাম মর্নিং এর ম্যাডাম
না ঢোকেনি
আমি মৈনাকদাকে ফোন করছি দাঁড়ান
হ্যাঁ মর্নিং এর ম্যাডাম কেউ ঢুকতে বলো
হ্যাঁ ঢুকতে বলছি আর বাকি অ্যাকসেপ্ট করছি
বাকিদের ঠিক রাখলেই বাস হয়ে যাবে
হ্যাঁ মৈনাকদা একটু ঢুকুন সবাই আছি হ্যাঁ হ্যাঁ মৈনাকদা ঢুকুন হ্যাঁ
হ্যালো
হ্যাঁ
দক্ষিণে করে না ইউটিউবটা না
শুনতে পাচ্ছেন হান্নানদা?
হ্যাঁ 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 শুনতে পাচ্ছি হ্যাঁ
হ্যাঁ এবার শুরু ময়না
রত্নাদি তুমি
দাঁড়া,
শুরু
দাঁড়া।
করো।
হ্যাঁ
দাঁড়াও, আসেননি তো এখনো।
হ্যাঁ
ম্যা-
এই সবাই আসবেন তারপর শুরু করবো তো।
হ্যাঁ 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 না এক মিনিট
হ্যাঁ,
হ্যাঁ
না না সবাই এখন আরম্ভ করো না, সবাই
হ্যাঁ,
আসুক আগে,
সবাই আসুক
জয়েন
আগে।
করুক।
হ্যাঁ, অন্তত প্রিন্সিপাল মৈনাকদার,
মৈনাক।
লনা মৈনাকদার, মুকুট এই
হ্যাঁ।
তিনজন তো আসবেই।
ওদের আগে জয়েন করতে দাও।
হ্যাঁ
হ্যাঁ, হ্যাঁ, ঠিক আছে,
ম্যাডামকে ফোন
ঠিক আছে।
করেছি, ম্যাডামকে ফোন করেছি। হ্যালো ম্যাডাম, ম্যাডাম চিন্ময় বলছি। আচ্ছা দেখতে পাচ্ছি না ম্যাডাম, এই জন্য। আচ্ছা আচ্ছা ম্যাডাম ওয়েট করছি আমরা। ম্যাডাম ঢুকছে এখন, বললো। আমি ইউটিউব চলছে, ইউটিউব রত্নাদি ইউটিউবটা চলছে, কিন্তু খেয়াল করো।
রত্নাদি তো বলবে।
হ্যাঁ, ইউটিউব চলছে।
চলছে তো? আচ্ছা,
দোলা
ঠিক আছে।
দেখছে, দোলা দেখছে,
আচ্ছা ঠিক আছে ঠিক আছে।
দোলা দেখছে, সব ঠিক আছে, ও ওকে করছে।
ঠিক আছে। হ্যালো ম্যাডাম বলুন। আপনাকে দেখতে পাচ্ছি না, রিকোয়েস্ট আসেনি ম্যাডাম, ওই জন্যই। মানে আপনি ওই লিঙ্কটাতে ক্লিক করুন, লিঙ্কটাতে ক্লিক করলে আমি এখানে অ্যাকসেপ্ট করে নিচ্ছি। ম্যাডামই ক্লিক করতে পারছে না, বললি না কি যে করি বল, ম্যাডাম ঢুকতেই পারছে না।
কেন?
ম্যাডাম তো বললাম তো সব, ম্যাডামের নাম্বারই দেখতে পাচ্ছি না।
ম্যাডামের কাছে গেছে তো লিঙ্কটা?
হ্যাঁ গেছে, আমি সকালেই পাঠিয়েছি তো।
আচ্ছা, লিংকে ওই হাইফেন গুলো বাদ দিয়ে লিখতে বলো, হাইফেন গুলো লিখলে অসুবিধা হয়।
কেন, আমি তো হাইফেন লিখলাম।
হাইফেন লিখলে আসতে চায় না।
ম্যাডামের ফোন আবার সুইচ অফ বলছে, কি করি বলো তো?
হ্যাঁ, কি হচ্ছে?
ম্যাডামের ফোন সুইচ অফ বলছে।
আর মুকুট
মুকুট তো ঢোকার কথা তো 6টার মাসে।
আর ওই মইনাদাও তো আসেনি।
আরে দেখো,
না,
চিন্ময়, চিন্ময় কিছু সমস্যা হচ্ছে মনে হয়, কেউ ঢুকতে পারছে না তো।
না ময়নাকদাকে বললাম তো, সমস্যা তো দেখতে সবাই তো অ্যাকসেপ্ট করছে গো।
কিন্তু আমরা কজন ছাড়া তো আর এখানে কেউ নেই।
হ্যাঁ,
আমি রিকোয়েস্ট গুলো ক্যান্সেল করছি, দেবনি না সবগুলো।
হ্যাঁ, এবার ক্যান্সেল করছো কেন?
ক্যান্সেল করো কেন? হ্যাঁ, accept
করে
করো।
দাও, করে দাও, অ্যাকসেপ্ট করে দাও। আচ্ছা ঠিক, করছি
সব
করছি।
অ্যাকসেপ্ট করো, অ্যাকসেপ্ট করো।
আচ্ছা করছি করছি।
হয়তো বোঝা যাচ্ছে না তো যে ঠিকঠাক করছে কিনা। তাহলে একটু 6টার পর থেকে শুরু করি রত্নাদি।
হ্যাঁ ময়নাকদা বলুন। হ্যালো ময়নাকদা। হ্যাঁ ওটা
মিটিং কোডটা দিয়ে ঢোকার চেষ্টা করছি।
ওই জাস্ট ক্লিক করুন, ওই লিঙ্কটাতে ক্লিক করুন।
হ্যাঁ
লিঙ্কটাতে ক্লিক করলে আমাকে চলে আসবে এখানে। হ্যাঁ 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 আচ্ছা আচ্ছা।
কেউ ঢুকতে পারছে না।
চিন্ময়কে অ্যাকসেপ্ট করো, তাহলে বোঝা যাবে
হ্যাঁ।
বাকি করতে পারছে কিনা।
তা ছাত্ররা সব পাঠাচ্ছে, বুঝলে কি করবো?
আচ্ছা, অ্যাকসেপ্ট করো, তুমি অ্যাকসেপ্ট
করো
করো,
না,
সব
যে
অ্যাকসেপ্ট করো।
যে
করে দাও
আসছে,
এখন।
হ্যাঁ,
হ্যাঁ,
যে আসছে তাকে অ্যাকসেপ্ট করে দাও।
হ্যাঁ ম্যাডাম বলুন। ম্যাডাম?
আমি কিন্তু ঢুকতে পারছি না, আমি এটা কিন্তু কি হয়ে মানে আমি প্রেস করেছি লিংকটা,
হ্যাঁ।
কিন্তু জয়েন দেখাচ্ছে।
ও ওটা ওটা আবার করুন তো।
আমি অনেকবার করলাম, আমি কিন্তু ঢুকতে পারছি না।
ও ওটাকে আবার, কিন্তু এখানে তো
আচ্ছা
আছে।
বলো না যে হাইফেন গুলো লিখেছে, আমার কিন্তু এটা অসুবিধা হয়েছিল। হাইফেন গুলো ওই হান্নান তারপর বললো যে হাইফেন গুলো লিখবেন না।
তুমি আগের লোকেদের জয়েন করিয়ে যাও, আগের লোকেদের জয়েন করিয়ে যাও।
হ্যাঁ ভাবলো
হ্যাঁ
এই চিন্ময় অ্যালাউ করো, জয়েন নাও করছে মুকুটদা, অ্যালাউ করো।
মুকুটদা করেছি, মুকুটদা হয়ে গেছে, মুকুটদা হয়ে গেছে।
মুকুটদা তুমি জয়েন হয়ে গেছো, জয়েন হয়ে গেছে। হ্যাঁ এখানে দেখাচ্ছে যে
এখন ওটা তুমি বন্ধ করে দাও।
পেয়েছো প্রেশার গুলো?
এখন আছে তো। এই,
হ্যাঁ সব
এখানে দেখাচ্ছে। এই চিন্ময়, চিন্ময় মুকুটদা তো জয়েন হলো।
হ্যাঁ মুকুটদা জয়েন হয়েছে মুকুটদা।
কি বলছো?
নামটা এখানে এসে এই চিন্ময়,
হ্যাঁ বলো 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 বলো।
এলারে
এখানে এসছে কিন্তু মুকুটদা বলছে মুকুটদা জয়েন হয়নি। মুকুটদার নাম এখানে এসছে তো, কিন্তু মুকুটদা বলছে মুকুটদা জয়েন হয়নি।
ও আবার পাঠাতে বলি দেখি মুকুটদা।
এখানে তো দেখাচ্ছে মুকুটদা,
মুকুটদা দেখাচ্ছে তো।
দেখাচ্ছে।
দুধ আছে তো ওখানে?
মায়ের ওইটা পেড়ে দিচ্ছে, আমি কিন্তু চেষ্টা করে দিচ্ছি, কোনো অসুবিধা নেই।
ও ঘরে ঘরে
কিন্তু ঘরে কাপড়ের মধ্যে বসে বলছে আমার
হ্যাঁ মুকুটদা, হ্যাঁ আচ্ছা আচ্ছা ঠিক আছে, দেখছি দেখছি।
কিন্তু মায়ের ওইটা ব্যবস্থা করতে চেষ্টা করতে
হ্যাঁ মনে হয় না।
তুই চলে যা, চলে যা এইবার।
দুধ আছে এখানে,
হ্যাঁ
চাল দেয়া
আমি
আছে।
আবার লিঙ্কটা পাঠাচ্ছি, দাঁড়াও আবার পাঠাচ্ছি।
ওটাকে নষ্ট করিস, আগে এটা ছিঁড়ে যাবে। এখানে নিয়ে যাও, ওকে এই এখন ভাই তাই নিয়ে যাও।
মুকুটকে তো দেখাচ্ছে।
মুকুটদা আছে বললো তো, মুকুটদা আছে।
এখন না, পরে আসিস, পরে পরে তোকে দেবো, সুযোগ দেবো। আর
তাহলে লনা
পরে
ম্যাডামের কি
সুযোগ
হবে?
দেবো,
ঢুকেছি
বন্ধ কর না।
এখন এসছি।
হ্যাঁ হ্যাঁ হ্যাঁ
প্রথমে
মৈনাক-
পাচ্ছিলাম না, এখন এসছি।
আচ্ছা আচ্ছা মৈনাকদা,
মনে রাখলে আবার পাঠালাম লিঙ্কটা আবার।
মুকুটকে দেখাচ্ছে না কেন?
মুকুটদা এসছে মুকুটদা।
এই যে নাম দেখাচ্ছে তোমাকে।
এই আছি আমি,
এই তো হ্যাঁ, মুকুটদা আছেন।
আছি।
6টা বেজে গেছে।
ম্যাডাম আপনাকে
গুড
পাঠিয়ে
ইভিনিং,
লিঙ্কটা আবার।
গুড ইভিনিং।
আমি আবার আপনাকে পাঠালাম ম্যাডাম। হ্যাঁ
মুকুট,
আমি তো আপনাকে দেখতে পাচ্ছি না ম্যাডাম।
হ্যাঁ দাদা, বলুন।
আসেনি আপনার থেকে কোনো।
গুড ইভিনিং।
আমার
গুড ইভিনিং।
সবাই কিন্তু জয়েন করে গেছে।
Good
ম্যাডাম।
evening.
আমি
গুড ইভিনিং।
আহ, আহ, কি মুশকিল তো সেটা। না আমি আবার পাঠাচ্ছি।
গুড ইভিনিং।
ঠিক আছে আবার পাঠাচ্ছি।
হ্যালো,
এর মধ্যে ঘুমের ওষুধ খেয়েছে। ওই যে
হ্যালো মুকুট।
হ্যাঁ বলুন।
হ্যাঁ গুড ইভিনিং।
যে বলি
এই
না,
ঢুকলাম।
গুড ইভিনিং।
হ্যাঁ
বলুন, গুড ইভিনিং।
থ্যাংক ইউ গুড ইভিনিং। এই পারলাম, এই যে ঢুকতে পারলাম। হ্যাঁ ঠিক আছে।
যে বলি না ম্যাডাম ঢুকতে পারছে না। ম্যাডাম আর মহিনা কি করা যায় বলো তো?
ঘরে খাটটা দিয়ে এই ঘরে করে দিলে বাথরুমটা জামে।
ওনাদের আসতে হবে তো।
অসুবিধা বলছে ওই লিঙ্কে ক্লিক করতে আস্কিং টু জয়েন হয়ে পড়ে আছে, কিন্তু বাকিরা কিন্তু অ্যাকসেপ্ট তো হচ্ছে বাকিদের। হ্যাঁ বলছে তো পাচ্ছে না, করি বলো তো স্যারকে সবাই কিন্তু জয়েন হচ্ছে, এতে জয়েন হতে পারছে না, করি বলো তো। হ্যাঁ ওটা প্রেজেন্টে সিকেন করবে তো। হ্যাঁ
হ্যালো চিন্ময়।
হ্যাঁ বলো 1 মিনিট আমি বলো
চিন্ময়।
হ্যাঁ
হ্যালো।
হ্যাঁ বলো
হ্যালো।
হ্যাঁ
হ্যালো, শোনা
হ্যাঁ
যাচ্ছে?
শুনছি, বলো।
হ্যাঁ শোনা যাচ্ছে।
আচ্ছা ঠিক আছে ওকে।
হ্যাঁ ম্যাডাম, হ্যালো ম্যাডামের লাইনও পাওয়া যাচ্ছে না।
হ্যালো বাসু দিদি। হ্যালো।
ভাস্বতীর ইয়েটা মাইক্রোফোন অফ আছে।
আচ্ছা।
হ্যাঁ ম্যাডাম হচ্ছে,
বলছি কোনটা অফ আছে রে?
তোর মাইক্রোফোন অফ ছিল, হান্নান কথা বলছিল তোর সাথে।
হ্যাঁ আমি উত্তর দিচ্ছিলুম। হ্যাঁ বলো। হ্যাঁ ভালো আছি।
আসুদি
হ্যাঁ
কেমন আছিস?
ঠিক আছি, একদম ঠিক।
কিন্তু আমার রিকোয়েস্ট তো আসছে নাকি? আচ্ছা আমি আবার পাঠাচ্ছি।
শুরু কটায় হবে?
6টায় তো
একই লিঙ্কে
এখনই। হ্যাঁ শোন না, ওনাদের বল না মোবাইলে সরাসরি করতে, ওই লিখতে গেলে ভুলভাল হয়। মোবাইল থেকে করতে বল, ছোট হলেও দেখতে তো পাবেন। পার্টিসিপেট।
চিন্ময়েরও তো অফ মাইক্রোফোন।
হ্যাঁ চিন্ময় এখন কোথায় আমি দেখতে পাচ্ছি।
দেখতে পাচ্ছি না ময়নাকদা আপনাকে, মানে যেটাই তো বুঝতে পারছি।
মোবাইলে তাড়াতাড়ি হয়ে যাবে।
হ্যালো ময়নাকদা,
মোবাইলে আবার তো অ্যাপ ডাউনলোড করা না থাকলে হয় না।
না আমি তো সঙ্গে করে নিলাম। এমনকি আমি প্রথমে ভুল করে ভিডিওটা অফ করে রেখেছিলাম, তারপর যখন বুঝলাম যে তোদের দেখতে পাবো না, সঙ্গে আমি আবার আনইনস্টল করলাম, করে এত কিছু করে ঢুকেছি। আবার ইনস্টল করে ঢুকেছি, কয়েক সেকেন্ড লাগছে। ডাউনলোড করতে হবে, গুগল মিটে তো আছে ওদের। হ্যাঁ
মিটিং জয়েন
দেয়া আছে, ওটা ক্লিকটা করলেই গুগল মিট নিজেই চলে আসছে।
আমার এখানে কারেন্ট চলে যাচ্ছে, সেটা একটা বিপদ, আমাকে দেখা যাবে না।
ও কারেন্ট চলে গেলে তো মুশকিল।
হ্যাঁ
কারেন্ট চলে গেলে আমাকে দেখা যাবে না, মুশকিল হবে। এই প্রায় কারেন্ট চলে যাচ্ছে এখানে,
যা
অনেকক্ষণ ধরে তো বুঝতে শুরু করে দিলেই তো হয়।
ম্যাডাম ঢুকতে পারে, কিন্তু সবাই ঢুকছে, আমি জানি না কেন।
বুঝতে পারছি না যে ওরা ঢুকতে পারছে না কেন রে।
হ্যাঁ চিন্ময় চেষ্টা করছি।
আমি চেষ্টা করি, কিন্তু ওরা দুইও ঢুকতে পারে না। ময়নাকদা হ্যাঁ
আচ্ছা ঠিক আছে।
ময়নাকদাও তো বোধহয় জয়েন করতে পারে।
অপারেট করতে পারি।
হ্যালো, হ্যাঁ বলুন। হ্যাঁ পাঠাও পাঠাও, তাড়াতাড়ি পাঠাও।
বাবা 6টা 7 হয়ে গেল।
আরে এখানে ট্রায়াল চলছিল, ট্রায়াল করছিলাম। পাঠাও, তাড়াতাড়ি পাঠাও, সবাই পাঠাচ্ছে।
আমরা এরকম ভাবেই বসে থাকি বরঞ্চ।
সেই
দেখে মুখগুলো তো দেখতে পাচ্ছি কতদিন পরে বলতো।
ভাস্কর, তুই একটু অন্ধকার লাগছে কেন তোকে?
হ্যাঁ
কি জানি ও আলোর উল্টো দিকে বসেছিলুম বলে। এখন দেখতো
আলোর উল্টো দিকে বসেছি। এখন
ঠিক
ঠিকঠাক
আছে,
আছে।
এবার ঠিক আছে।
এবার আগের
তোকে না
থেকে
দেখতে
better।
পেলে কি করে হবে?
কেন হচ্ছে ডাক্তার, একটা পজিশন দেখে বল কোনটা ঠিক। ঠিক আছে, এবার ঠিক আছে।
এইটা better,
এইবার
এইটা
ঠিক
better।
আছে, এইবার ঠিক আছে, একদম একদম ঠিক আছে।
ম্যাডাম তো ঢুকতেই পারে না, কি করবো? হ্যাঁ বলো। ম্যাডাম তো ঢুকতেই পারে না, কি করি বলো তো ম্যাডাম আর মৈনাকদা?
ম্যাডামকে ফোন
বলছি
থেকে
মহিলা
বল।
কি
ল্যাপটপে করছেন, ফোনে না ল্যাপটপে?
মৈনাকদার ম্যাডাম তো ঢুকতেই পারছে না।
ওই দুজনকে ফোন থেকে
হ্যাঁ।
করতে বল।
দাও দেখি। হ্যাঁ, হুম। হ্যাঁ হ্যালো, আমার কাছে ম্যাডাম রিকোয়েস্টই আসছে না, কি করি বলুন তো? হ্যাঁ,
ফোন থেকে করছেন না ল্যাপটপ
ভারতী
থেকে?
ঢুকেছে দেখলাম, ভারতী বুঝছেন, একই লিঙ্ক তো পাঠাচ্ছেন এবার।
দুজনকে ফোন থেকে করতে বল। ফোন করে
হ্যাঁ ম্যাডাম, বলছি ম্যাডাম ফোন থেকে একবার চেষ্টা করুন না, ফোন থেকে ওই লিঙ্কটাতে ক্লিক করুন না একবার। ও ফোন, ও হ্যাঁ, ও আচ্ছা, কি জানি আমি তো আমি দেখতেও পাই না ম্যাডাম আপনাকে এখানে।
প্রথম হলে আমার তো সেই প্রথম দিন কত অসুবিধা হয়েছিল, মানে
মনে একটা ফোন থেকে একবার চেষ্টা করুন তো, আসছে না, রিকোয়েস্টই আসছে না ম্যাডাম।
কি গুগল অ্যাপ চিন্ময়?
হ্যাঁ হ্যাঁ ম্যাডাম ম্যাডাম ফোন করে, 1 মিনিট দাঁড়ান তো। হ্যাঁ ম্যাডাম বলুন। হ্যালো, নাম কি নামে আছে ম্যাম? নাম আসছে না মানে, না ম্যাডাম আসছে না, না আপনার নাম, না ম্যাডাম আসছে না ম্যাডাম, দেখি দেখতে পাচ্ছি না, এই জন্যই তো। আরেকবার পাঠান তো, আরেকবার পাঠান তো দেখি, এখন পাঠান। আমাদের রিকোয়েস্টই আসছে না ম্যাডাম। এখনো কোনো রিকোয়েস্টই আসছে না ম্যাডাম।
চিন্ময়?
হ্যাঁ ম্যাডাম, এই হ্যাঁ স্যার বলুন।
হ্যালো, হ্যাঁ চিন্ময় বাবু।
চিন্ময়?
হ্যাঁ 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 বলুন বলুন। হ্যালো,
চিন্ময়
হ্যাঁ হ্যাঁ বলুন স্যার।
বলছি যে একটা কাজ করো না, ওনাদের যদি একটু পরে জয়েন করে লাস্টের দিকে যদি বলে দেওয়া যায়, বা যদি এটাকে ওনারা ফোনে বলতে পারবে, মৈনাক বা ফোনে বলা যাবে?
আমি দেখতেই পাচ্ছি না ওদের স্যার, আমি ওদের দেখতেই পাচ্ছি না।
কেন?
বাকিরা তো জয়েন,
ওরা আরেক
কি করি বলো তো, কি করি বলো তো, দেখতে পাচ্ছি না আমি কিন্তু ওদের।
মাইক্রোফোন অন করো।
কি করবো? হ্যাঁ মৈনাকদার ম্যাডাম জয়েনই হতে পারছে না তো। হ্যাঁ ম্যাডাম বলুন। হ্যাঁ হ্যাঁ বলুন বলুন বলুন। না ম্যাডাম দেখতে পাচ্ছি না তো। আজকে কিন্তু জয়েনের দেখতে পাচ্ছি না।
চিন্ময়, আমার আমার মনে হয় তুই একটু লোকজনকে জানা যে যারা জয়েন করতে পারছে না তারা ইউটিউব লিঙ্কটা দেখুক, কারণ প্রচন্ড এই নিয়ে আমাদের যে পিসিপিএফ গ্রুপ আছে সেখানে লোকজনের লেখালেখি করতে দেখছে, প্রচুর কনফিউশন মানুষের মধ্যে আর কি। অ্যাটলিস্ট কিছু একটা বললো, মানে দে আর ভেরি কনফিউজড আর কি।
হ্যাঁ আসলে দেখতে পাচ্ছি না, এবার মুশকিল তো হয়ে গেল ম্যাডাম। আরে মৈনাকদা
না না ম্যাডামের কথা আমি বলছি না, বলছি যারা আমাদের পিসিপিএফ ফোরাম আছে, এবার সেই ফোরামের আমাদের যে গ্রুপ তাতে লোকজন লিখছে তারা পারছে না, অ্যাটলিস্ট তাদের ইউটিউব লিঙ্ক কিছু শেয়ারটা করে দেবে আরেকবার 2 নাম্বার করে আর কি। এবং সেটা মুখে জানিয়ে দিতে লিখে দেতা তোরা,
আমি লিখে গ্রুপে লিখে দিচ্ছি।
চিন্ময়,
হ্যাঁ
তুমি
এখানে তো অলরেডি 94 হয়ে গেছে।
হ্যাঁ 94 হয়ে গেছে তো।
আচ্ছা মেল থেকে ডাইরেক্ট মেলে পাঠিয়ে দাও, মেল থেকে ওই লিঙ্কটা ডাইরেক্ট ক্লিক করলে আসছে, তাহলে আসছিল না, আমারও ছিল সেটা। মেল থেকে ডাইরেক্ট যদি করা হয় আসছে, টাইপ করলে আসছে না।
ঠিক আছে দেখছি ঠিক আছে, আমি লিখে দিচ্ছি, গ্রুপে লিখে দিচ্ছি, ঠিক আছে।
হ্যাঁ, একদম ডাইরেক্ট লিখে দাও, ওখান থেকে ডাইরেক্ট টাইপ করলে চলে আসবে।
হ্যালো চিন্ময়,
হ্যাঁ
হ্যালো
হ্যালো।
চিন্ময়, বলছি তুই গ্রুপে যেটা দিয়েছিস না, ওই গ্রুপের লিংক থেকে ডাইরেক্ট ঢুকতে বল ম্যাডামকে, ওখান থেকে হয়ে যাচ্ছে।
একদম ডাইরেক্ট
আস্কিং টু জয়েন বলছি, ম্যাডাম হচ্ছে না।
না, ওই ডাইরেক্ট লিংক থেকে করতে বল।
দিয়ে ইউটিউবে
ম্যাডাম গ্রুপে নেই তো।
তাহলে মেলে যে লিংকটা পাঠানো হয়েছে না, ওইখান থেকে ডাইরেক্ট ঢুকলেই চলে আসবে,
নাহলে অসুবিধা হচ্ছে আর কি। ঠিক,
হ্যাঁ আমি তো ভাবেই করলাম।
চিন্ময়বাবু, হ্যালো
হ্যালো।
হ্যাঁ, আমি আপনাকে একটা ওপিনিয়ন দিচ্ছি, একটু যদি কাজে লাগে আর কি। সেটা হচ্ছে আমি সুমন বলছি বসিরহাট কলেজ থেকে।
হ্যাঁ বলুন।
সেটা হচ্ছে যে লিঙ্ক ওনারা যেটা বললেন সেটা আমারও কিন্তু হচ্ছিল না, মানে মেল থেকেও কিন্তু ঢুকতে পারছিলাম না। ফলে এটা বেস্ট হবে আপনি ওনাদেরকে বলুন যে লাস্ট যে 3টে গ্রুপিং যে কোড আছে, সেই 3টে গ্রুপিং কোডে কোড এন্ট্রি করতে বলুন, মানে লিঙ্কে একসাথে লিঙ্ক এন্ট্রি করলে কিন্তু ঢুকতে পারবে না।
আচ্ছা
মানে দুটো উপায় থাকে, একটা হচ্ছে যে মেল ডিরেক্ট পুট করে ঢোকা যায়, কিন্তু ওটাও হচ্ছে না। একদিন বললেন ঢোকা যাচ্ছে, কিন্তু আমি কিন্তু এতক্ষণ পরে ঢুকলাম। আচ্ছা, আর একটা অপশন আছে যে ওই লিঙ্কে যে 3টে গ্রুপিং করে যে 9টা কোড আছে গ্রুপিং করে, সেই কোডকে কপি করে ডিরেক্ট লিঙ্কে বসাতে বলুন, তাহলে হয়ে যায়।
আচ্ছা ঠিক আছে,
ওটা বললেও হয়ে যায়।
বলছি
লিঙ্কটা না বসলে হবে না কিন্তু।
হ্যাঁ ম্যাডাম, ম্যাডাম ওই লাস্টে যে কোডগুলো আছে না, ওইখানে একটু ওইটা লিখে টাইপ পাঠান না দেখি, লাস্টে যে কটা কোড আছে ওইটা, ওই যে এখানে যে এন্টার কোড বলে যে অপশনটা আছে,
আমি তো ল্যাপটপে করছি না, আমার তো কোড দেখাচ্ছে। হ্যালো,
হ্যাঁ শুনতে পাচ্ছি ম্যাডাম। দেখতে হ্যাঁ বুঝতে, কিন্তু নেই ম্যাম, পাচ্ছি না ম্যাডাম। হ্যাঁ ল্যাপটপে ঢুকুন তো, এটা টাইপ করে। ঠিক আছে। হ্যাঁ না, আমি ওয়েট আপনার জন্য ওয়েট করে আছি ম্যাডাম, এই জন্য। হ্যাঁ ঠিক আছে ঠিক আছে। মনাকদা, হ্যাঁ মনাকদা বলুন। এই তো আপনি জয়েন হয়ে গেছেন, করে দিয়েছি। হ্যাঁ করে দিয়েছি আপনাকে, দেখুন। হ্যালো ম্যাডাম।
হ্যালো বৈনাকদা, কেমন আছেন?
হ্যালো ম্যাডাম
হয়েছে তো, হয়েছে না?
হ্যালো ম্যাডাম,
জয়েন করেছি তো
বৈনাকদা, দেখতে পাচ্ছেন?
শোনা যাচ্ছে?
হ্যাঁ
শোনা যাচ্ছে।
শোনা যাচ্ছে। হ্যাঁ
আচ্ছা ঠিক আছে। কি বাসতি?
হ্যাঁ বল।
ঠিক আছিস তো?
একদম ঠিক।
গুড।
ময়না, কি হয়েছিল?
বল।
কি হয়েছিল? ঢুকতে পারছি, ঢোকা
আমি
অসুবিধা
জানি না
হচ্ছিল
কিছুতে
নাকি?
হচ্ছে কিনা। হ্যাঁ
আচ্ছা
চিন্ময় শুরু করবে নাকি?
হ্যাঁ শুরু করে দিই।
দেরি হয়ে যাচ্ছে অনেক তো।
শুরু করে
হ্যাঁ,
দাও।
হ্যাঁ, শুরু করে দাও, অনেক দেরি হয়ে যাচ্ছে। শেষের আগে উনি বলে দেবেন নাকি?
ঠিক আছে।
এরা এরা দেখো নিজেদের মধ্যে কথা বলছে।
শুরু করে দেবো না, শুরু করো।
হ্যাঁ রত্না কি করবে?
ম্যাডাম আসতে পেরেছেন?
ম্যাডামকে বলছি, খবর পাঠাচ্ছি।
আমরা শুরু করবো স্যার, 6:23 বাজে।
করবে, ম্যাডামকে তো দরকার, কিন্তু ঠিক আছে তোমরা শুরু করো, অনেকটা হয়ে গেছে তো সবাই এবার।
রত্নাদি তাহলে শুরু করে দাও।
Hello, am I audible?
Yes. Yes.
Good evening, everyone. Wishing you all a very happy Independence Day. Principal of RBC College, IQAC Coordinator of Rishi Bankim Chandra College, and our respected speaker are here in Google Meet platform. So we are going to start the webinar. Participants on Google Meet are requested to mute themselves and turn off their video mode for the entire session of the webinar.
Am I audible?
Yes.
Am I audible?
Yes.
In these trying and unprecedented times, as we celebrate our country's 74th Independence Day, let us pledge to serve our nation in whatever small way we can to help in nation building. With freedom in the mind, faith in the words, and pride in our souls, with the dark clouds of the pandemic hovering over us and no end in sight, Lord, we pray for our countrymen, heal us, save us. Let us all join to pay our respect for our loving country, requesting all to stand and stay in tune with the national anthem.
হ্যাঁ হ্যালো,
হ্যাঁ আমি ঢুকে গেছি চিন্ময়।
আমি অ্যাড করে দিয়েছি আপনাকে।
ওকে, থ্যাংক ইউ।
এই দেবলি না?
বলো।
হ্যালো
হ্যাঁ বলো।
হ্যালো
বলো।
হ্যালো,
বলছি গান শোনা যাচ্ছিল না তো? শোনা গেছে?
হ্যালো
শোনা গেল না গান?
হ্যাঁ হ্যালো,
আমি তো পাইনি।
না শোনা যায়নি।
হ্যালো
না শোনা যায়নি।
আচ্ছা,
যায়নি।
এই চিন্ময় কোথায়, কে বলছে? হ্যালো
স্যার শুরু করুন এবার শুরু করুন।
প্রিন্সিপাল
করে দে বাবা, আর দেরি করছিস।
Respected Prince-
without wasting any time, okay, so let us start.
Respected Principal of Rishi Bankim Chandra College for Women, also present here. So please take your seats. On behalf of the Department of Chemistry, Rishi Bankim Chandra College, Noihati, I, Dr. Ratna Datta, cordially welcome all of you to the state level webinar on optical methods of analysis as per UGCBCS curriculum of West Bengal State University, Barasat. First of all, I am pleased to welcome our esteemed guest and today's speaker, Dr. Mukut Chakraborty. I also welcome our Honorable Principal Sir and patron of this webinar, Dr. Sanjeev Kumar Saha of Rishi Bankim Chandra College, Dr. Lona Mukhopadhyay, respected Principal, Rishi Bankim Chandra College for Women, and also Dr. Moinak Roy, IQAC Coordinator, Rishi Bankim Chandra College. Finally, I heartily welcome all the participants who have joined us on Google Meet, as well as all those who are listening to us on YouTube live streaming of this seminar. Thank you all for showing interest in our program. Participants on Google Meet are requested to mute themselves and turn off their video mode for the entire session of the webinar. Participants may ask questions through Google Meet chat box and YouTube chat box. At first, I am requesting Honorable Principal of Rishi Bankim Chandra College, Dr. Sanjeev Kumar Saha, to deliver his inaugural speech.
Good joy.
Okay. Good evening, everybody. Can you hear my voice? Yes.
Yes.
Can you hear? Okay.
Yes.
Okay. Thank you. So today is a special day for us. Happy Independence Day to all of you. Respected Principal, RBC College for Women, Dr. Lona Mukhopadhyay, and Dr. Moinak Roy, Coordinator, IQAC of the college, and our other teachers and honorable speaker of this webinar, Professor Dr. Mukut Chakraborty, who was also a former GB member of our college and very much close to me, and respected teachers of other colleges, participants, and finally my esteemed colleagues and the students of my beloved students. We, the Department of Chemistry and IQAC of our college, in collaboration with RBC College for Women, we have organized this webinar, and we know very well that the last few months we are passing a very hard time, and due to this our global infection of coronavirus, we know very well this we are practically confined within our residence. School and colleges are
শোনা যাচ্ছে না স্যার?
closed.
শোনা যাচ্ছে না।
Students have no opportunity to get their classes, so we have arranged. Hello. শোনা যাচ্ছে?
এবার শোনা যাচ্ছে।
শোনা যাচ্ছে?
হ্যাঁ।
Yes, you are audible.
Hello. Can you hear? Everybody
Yes, yes.
can't hear. Hello?
শোনা যাচ্ছে
Yes, sir.
সঞ্জীবদা?
Yes, yes. হ্যাঁ বলুন, শোনা যাচ্ছে। এখন আবার শুনতে পাচ্ছি না।
ওনার নেটের কোনো প্রবলেম হচ্ছে না।
শোনা যাচ্ছে?
হ্যাঁ,
শোনা যাচ্ছে, বলুন।
হ্যাঁ হ্যাঁ
বলুন স্যার।
হ্যাঁ বলো দুর্জয়।
শোনা যাচ্ছে?
হ্যাঁ
ওকে।
হচ্ছে তো? প্রথম যে একটু প্রবলেম হচ্ছিল জানো তো, হ্যাঁ দেখতে পাচ্ছ তো? হ্যাঁ ঠিক আছে ঠিক আছে। হ্যাঁ 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 আর অ্যালাউ করা যাবে। ঠিক 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 আছে ঠিক আছে ঠিক আছে
maybe some internet issue,
ঠিক আছে ঠিক আছে ঠিক আছে ঠিক আছে তুই লাইনে থাকো
maybe there are
লাইনে
technical
থাকো।
fault.
Being a student of chemistry, I just
দেখছি
some
হ্যাঁ,
words on
আচ্ছা,
the
ঠিক আছে
topic.
ঠিক আছে
We know that the topic is very interesting, that is the optical methods of analysis. So it is a major part of modern instrumental analytical chemistry. Focuses. Just give you some word. Hello. শোনা যাচ্ছে রে? Hello.
হ্যাঁ যাচ্ছে
এখন
যাচ্ছে
যাচ্ছে, এখন যাচ্ছে।
শোনা যাচ্ছে। হ্যাঁ
Acha. So it is very unfortunate that due to this system I can't say properly. So we have with us a very eminent speaker, Dr. Chakraborty, who will give us an idea about this topic, and we know that he will also give an idea about the atomic absorption spectroscopy, which is very interesting, and we know that this is a spectroanalytical method for the quantitative estimation of metal ions, qualitative and also quantitative. So it has various applications nowadays, and we know, and I just request to the students hear properly and keep notes. So without any wasting any time, I just stop here, and thank you very much again on behalf of the department and on behalf of the college. I just congratulate you and convey my heartiest thanks to all of you to join this webinar. Thank you very much.
Thank you, sir. Next, I request Honorable Principal of Rishi Bankim Chandra College for Women, Dr. Lona Mukhopadhyay, for welcome address.
থ্যাংক ইউ রত্না। am I audible? শোনা যাচ্ছে?
Yes,
yes,
হ্যাঁ শোনা যাচ্ছে।
Hello everybody, a very good afternoon. I am Dr. Lona Mukhopadhyay, Principal of RBC College for Women. My best wishes to all on the 74th Independence Day. I thank Dr. Sanjeev Saha, Principal of RBC College, and my friend Dr. Ratna Dutt, Associate Professor of Chemistry of RBC College, for inviting me on behalf of my college to collaborate this webinar. And it is my pleasure to be a part of this webinar, and I am privileged and honored to welcome Professor Mukut Chakraborty, Professor of Chemistry of WBSU, that is West Bengal State University. He will be speaking on the topic optical methods of analysis, which is in relevance with the chemistry honours syllabus, and students as well as teachers will be benefited from his lecture. I also welcome Dr. Moinak Roy, IQAC Coordinator of RBC College, conveners Chinmoy Bishwas and Dr. Debolina Mitro, and all other teachers of RBC College chemistry departments and students of chemistry departments, and also all participants present here from different colleges. I welcome them all in this webinar. Organizing the webinar has a number of advantages, and online teaching process is going on due to total lockdown in education sector due to COVID pandemic. So webinar serves a platform for exchanging the views of students with the teachers and students as well as teachers are benefited from this webinar. Enlightening speech of Professor Chakraborty will enhance the skill of students, and I wish a great success of this webinar. Thank you all. Thank you.
Thank you, ma'am. Now I am inviting respected IQAC coordinator, Ms. Ubung, brief introduction about today's webinar. Dr. Moinak Roy.
হ্যালো
হ্যাঁ স্যার শোনা যাচ্ছে, বলুন।
শোনা যাচ্ছে?
হ্যাঁ হ্যাঁ
হ্যালো
হ্যাঁ হ্যাঁ শোনা যাচ্ছে, শোনা যাচ্ছে, হ্যাঁ শোনা যাচ্ছে।
Okay, at the very outset, I would like to express my deep regards to this department and my feelings. I am feeling very much proud and privileged to be invited to speak a few this webinar. However, the subject is not my cup of tea. Still, being the coordinator of IQAC cell, I would like to say a few words for this seminar. When I joined in this college on 1992, the Department of Chemistry of this college was one of the biggest department, and so far I can remember, it is at least no less than 16 teachers were engaged teaching in this department. And quality of teaching was so high that it was regarded as one of the best teaching faculties in the state. Now, naturally, in course of time, the size in terms of faculty members, it has shrinked. Still, the quality of teaching is undoubtedly one of the best teaching in our university, so far my own estimations. New teachers, a brand of new teachers has joined this college, and they are trying their best to offer the past glory of the department with their enthusiasm and relentless untiring effort to serve the interest of the teaching students community. This is quite expressive from the choice they made in selecting the topics. The topic is very much included in the syllabus of this university, and they have chosen a person whom I personally knew since last 10 years or so. Is quite, not only quite efficient, he is very much students friendly and popular among students, and I hope Dr. Mukut Chakraborty of West Bengal State University will serve the interest of the students, and the department has selected Dr. Chakraborty to be a speaker on the subject. I think this will be quite interesting, though I will not be able to just get a flavor of this talk, since I do not have any background of the subject. Still, this is my expectation that the seminar will reach at its height and it will be a grand success for the organizers. Thank you.
Thank you, sir. Finally, I request Dr. Sheikh Hannan Mondol, Associate Professor, Department of Chemistry, Rishi Bankim Chandra College, introduce our distinguished speaker, Professor Dr. Mukut Chakraborty of West Bengal State University, to our esteemed audience. Hannan, please take over.
Okay, hello. I am audible?
Yes.
Okay. Good evening, everyone, and happy Independence Day. I am Dr. Sheikh Anand Mondal. I am privileged to introduce Professor Dr. Mukur Chakraborty of Department of Chemistry, West Bengal State University. He has finished his BSc from Presidency College, MSc from Calcutta University, MBA from Indian Institute of Social Welfare and Business and Management. He did his PhD from Indian Association for the Cultivation of Science, Yadipur. He is the recipient of Professor Sadhan Bose Memorial Award, recipient of Sir P.C. Rai Research Award, Convention Award for Young Scientists from Indian Chemical Society, and Shiksha Ratna of Government of West Bengal. Maharaja Manindra Chandra College, Kolkata from 2001 to 2009. And later he joined the Department of Chemistry, West Bengal State University in the year 2009, and presently he is the professor of this same department. His major research interests are conduct polymer synthesis and characterization, synthesis of materials based on nanoparticles, graphenes, and these materials having electronic and anti-cancer applications. Among his other interests are absorption of water-soluble dyes from wastewater, fluorescence studies of nanoparticle system. He has published both in international and national journals more than 80 papers, and their average impact journals have average impact or approximately 3. Moreover, he bears several academic and administrative responsibilities: subject expert, project advisory committee, West Bengal BST, reviewer and member of editorial board of different national, international journals in chemistry. He is the coordinator of NAC chairing committee of West Bengal State University. He is also the ex-chairperson, as we all know, the UG Board of Studies, PG Board of Studies, and Board of Research Studies in Chemistry, West Bengal State University. He has also served as the chairperson and member of different academic and administrative committees of West Bengal State University and other universities. Professor Mukur Chakraborty, please continue your lecture. Professor Mukur Chakraborty.
To Dr. Anand Mondal for your introduction. I don't think I need so many formal, because almost all of the participants out over here are very close to me and very known to me over maybe the last 10 to 15 years. And keeping that in mind, I would, on behalf of Rishi Bankim Chandra College, would personally apologize to many of my colleagues and friends who have been writing on the different forums that they cannot enter this webinar for certain technical reasons. I mean, there are many of them who call me by my first name and they talk to me as Tui. So I personally am sorry that I am overwhelmed by the response that all of my friends and colleagues have shown, and it was really heartening to know the number of participants who wanted to listen. I don't know whether I'm worth that, because when Sanjeevda called me up the first day asking me to talk on some method of spectroscopy, I thought I would be talking on fluorescence or maybe UV visible, which are areas on which I have worked personally. And Then I received a call from Shoma. Shoma is unfortunately not here today. Her mother is not well. And Shoma told me, no, Mukutta, you have to talk on something related to the undergraduate topic and back to this particular portion. So initially I thought I'll talk on both UV visible and atomic absorption. Then I thought maybe a time span of 1 hour would be, maybe 1 hour 15 minutes would be too much to cover both the topics. So I'll be primarily concentrating my discussion today on atomic absorption spectroscopy. And with these few words, let me go to my presentation.
স্যার আপনার মাইক্রোফোন আর যেটা বন্ধ করুন স্যার, আওয়াজ হচ্ছে মাইক্রোফোন আর ক্যামেরাটা।
Can you see this? Is it visible to everyone? Hello? Is the presentation visible to everyone?
Yes. Mukunda, শোনা যাচ্ছে।
Thank you.
No.
No, presentation we cannot see.
In that case, you pin this particular screen, and I would request others to kindly keep the microphone in mute mode.
ভার্সিটি মাইক্রোফোনটা অফ কর।
I'll be talking on optical methods of analysis. So by this, what I plan to talk about today would be flame atomic absorption and flame emission spectroscopy. The thrust area would obviously be the undergraduate syllabus of West Bengal State University. Now, the moment you come to this topic, though we have only the word flame written in our syllabus, it is very difficult to differentiate between flame and non-flame, because the moment you're talking about these kind of spectroscopy, you need to do an atomization process. And in this atomization process, the flame and the non-flame techniques, they go hand in hand. And so I'll be talking both on the flame and the non-flame techniques. With just major thrust area would definitely be the flame techniques. Excuse me. Next would be, see, there is an emission spectroscopy. Now, we have all done emission spectroscopy throughout our lives. So I'll have a very brief, I would say, preliminary discussion on emission spectroscopy before I go into the main topic. And I would try to identify the different components which are there in the syllabus for atomic absorption spectroscopy, keeping in mind the different areas which are there. Is the screen visible to everyone?
No, the screen is not visible, Mukunda. Screen is not visible. Please present now. Click on the present now.
Screen is not visible.
No, Mukunda.
Just a minute. Next. Just. Is it now visible?
No, Mukunda. আসছে না, স্ক্রিনটা
না,
আসছে না।
দেখা যাচ্ছে না, যাচ্ছে না।
দেখা যাচ্ছে না?
না।
দাঁড়াও, আরেকবার তাহলে দেখি। A second. Just give me a second.
মুকুট, আমি দেখতে পাচ্ছি।
এবার দেখা যাচ্ছে?
ঠিক আছে।
হ্যাঁ, এবার দেখা যাচ্ছে। তুমি ওটা ফুল স্ক্রিন করে দাও।
হ্যাঁ, ফুল স্ক্রিন আমি করে দিচ্ছি। দেখা যাচ্ছে কিনা আগে বল।
হ্যাঁ,
দেখা যাচ্ছে।
দেখা যাচ্ছে। ঠিক আছে।
দেখা যাচ্ছে।
যদি দেখা না যায় একটু বলিস, আমি একটু বুঝতে পারছি না দেখা যাচ্ছে না যাচ্ছে না কি সেটা।
ঠিক আছে।
মুকুন্দা ঠিক আছে মুকুন্দা।
না, দেখা যাচ্ছে।
হ্যাঁ দেখা যাচ্ছে
দেখা
পুকুর।
যাচ্ছে না,
ঠিক আছে,
আমরা দেখতে পাচ্ছি
আছে
না।
দাদা,
রত্না বলছি, রত্না দত্ত, আমরা দেখতে পাচ্ছি না।
আপনি পিন করে নিন রত্নাদি তাহলে স্ক্রিনটাকে।
পিন করাই আছে।
বাকিদের কি বক্তব্য?
হ্যাঁ হ্যাঁ দেখা যাচ্ছে।
মুকুটটা দেখা যাচ্ছে, মুকুটটা
দেখা যাচ্ছে,
দেখা যাচ্ছে, মুকুটটা দেখা
এখন
যাচ্ছে।
আগে দেখা যাচ্ছে, ঠিক আছে,
একবার হয়ে যাচ্ছে।
ঠিক আছে, ঠিক আছে, ওকে।
হ্যাঁ হ্যাঁ এবার দেখা যাচ্ছে, দেখা যাচ্ছে।
So this would be my plan of discussion for this evening. And so what exactly is spectroscopy? Now we have all done this since we were kids, practically high school level. So you have something which is there in the ground state. We take it to the excited state. This must be accompanied by some form of energy which is supplied to the element, to the atom, to the electron which is there in the ground state, and then you take it to the excited state. So this process is always associated with a supply of energy where we transfer a particle from a ground state to an excited state, and we know this is known as an excitation process. And we also know that such excitation processes are always induced processes. That is, the process can only take place if this energy is supplied to the system. That is, the energy acts as the stimulus for the process to take place. On the other hand, if we have an electron in an upper excited level, if it comes down to the ground state, this process is known as a decay process or an emission process. Now, since we are talking about spectroscopy, so we assume that the energy which is coming out is in the form of light. So we call this as a light energy. And for what we have studied till now, these are spontaneous processes. This is very natural that if we want to take, say you want to, basically you use a pump to raise the water from your ground level to the tank which is on the 3rd floor of your house. So this is an excitation process. The pump is the inducing factor, whereas we just open a tap and the water from the top level, the tank, it comes down. So anything coming down is a spontaneous process. That means it occurs naturally to us. We as chemists, we often represent it in this particular fashion. So we have energy level diagrams like this. The lowest level is known as the ground state, where we supply energy, and there is a transfer from the ground state to the different available excited states. The reverse, where the molecule or the electron comes down from the excited states to the ground states, emitting energy. For the time being, we are only concentrating on light energy. So these such processes are known as emission processes. This is fundamental excitation and emission process, which we have all studied since class 9, 10, since basic. So what exactly is critical about these processes? When we are talking about an absorption or an excitation process, the most important criteria is that you need energy of the right magnitude. Unless and until you supply energy which is comparable to the energy gap between these two levels, the promotion of an outer electron or the promotion of a particle from a ground state to an upper excited state will not take place. So for an absorption process, the guiding parameter, the guiding condition would be supplying the proper amount of energy, or you have the right wavelength to transfer a particle from a ground state to an excited state. This is very important when we are talking about atomic absorption. And in case of emission, we have a wavelength of light emitted when a particle is coming down from, now suppose, let us assume that a particle is coming down from the 2nd level to the ground state, and a particle is coming down from the 1st level to the ground state. In both the cases, we will have two different wavelengths of light which are being emitted, and these two wavelengths of light would be dependent on the material from which emission is taking place. Now, we all know that such spontaneous emission of light from an upper excited level to a ground state occurs by a process which is known as fluorescence. But when we are talking about fluorescence, it is also important to mention that fluorescence only occurs from the lowest excited level to the ground state. That is from 2 to 1 if we consider 1 as our ground state. Fluorescence normally does not occur from upper excited levels to the ground state. This is a normal condition. However, we have another type of emission which we observe, I would say, which is known as a laser. That is again an emission, but that is an emission which is an induced emission of light from an upper excited level to a lower level. So this is light amplification by stimulated emission of radiation. So the stimulus is already there in the acronym which is used for laser. So these are primarily, we always keep in mind, so the absorption is basically an induced process. For an emission, we can have both an induced as well as a spontaneous process. Normally, what we always see around us is a spontaneous process. Now, see, we are talking about emission of light. So whenever we are talking about emission, this will only be possible if we, prior to emission, we have an excitation. So unless and until we transfer the electron to an upper level, emission process will not take place. So for emission to take place, it is imperative that this must be followed prior by an excitation process. Now, we know about, we take a reaction in a beaker and we heat the beaker. So that is a type of a thermal excitation. We have studied about photochemical excitations where we carry out a reaction using UV light. We know about chemical excitation processes, electrical processes, electrochemical processes. So these excitation processes are processes which we have always, do, or maybe which we have always seen around us. On the other hand, when we are talking about
I think the presentation could not be seen now. Actually, one of them had started present now, and so his screen has started.
No, Paul is presenting now.
Now it has come.
Nah,
somebody else is sharing probably.
তুহিনা পাল, তুমি কিন্তু প্রেজেন্ট করে দিয়েছো স্ক্রিনটাকে, একটু বন্ধ করো। তুহিনা পাল
এবার এসছে?
Okay.
So when we are talking about atomic absorption, the primary process for an atomic absorption to occur is you need a process which is known as atomization. Atomization is nothing but you are producing small droplets of the particle which you want to study under atomic absorption. And this atomization process occurs by both, as I was telling you earlier, by non-flame techniques as well as flame techniques. So under the non-flame technique, you have an electric arc and an electric spark. I'll briefly tell you what these are. You have the flame techniques, which is the thrust area of a syllabus, and you have plasma. So we are all, you really don't talk about an MS unless we say it's an ICP-MS. So plasma is something which is almost these days synchronous with any good instrument that we are using. So these are different methods by which we are basically transferring a particle from a lower energy level to an upper energy level. Now, just as I was telling you that we have all done emission spectroscopy, I think all of us have done a flame test in our lab. Now, what exactly was the flame test that we did in our lab? We took a sample in that, and then we evaporated it in the non-luminous part of the flame and got a characteristic color. So from the color of the sample, we said, well, this might be sodium, this is strontium, this is calcium, and we had all these derivations, and that was one test probably which we never got wrong. We were more or less flame test. We missed out the radicals for the other tests, but for the flame test, unless the interfering radicals were there, we usually got the flame test right. So why did we get it right? We got it right because all these elements have a characteristic emission spectrum. So what we were practically looking at, we were looking at the transition of species from an upper excited state to a lower excited state, in the process giving out a characteristic element. Now, the problem came when we were dealing with mixtures. So we had a combination of calcium, strontium, and lithium. Often it was difficult to identify with the naked eye. But if you do it spectrophotometrically, you will obviously get 3 independent lines, and you can very easily say, well, this is for this is for this, and this is for that. So this was something. So emission spectroscopy is nothing but a characteristic emission of a particle when there is a transition from an excited level to a ground level. Now, what are the different types of emission spectroscopy which we normally observe? We observe a continuous spectrum, which is given out by incandescent solids. We have the band spectra. When we excite a molecule to a higher level, which is not thermally stable, so we get a band spectrum. And our primary line or our primary area of interest was always these line spectra, where we got this specific wavelength, specific lines, where we could identify what was there in the sample and what was it. But the only problem with these kind of estimations was that these were all qualitative estimations. We could only say that this is present and this is not present, but we could never say how much was the amount which is present in these kind of experiments. So if we just brush up what we did, now the problem was, say, suppose we need a transition from a ground state to the first excited state. The energy difference is maybe 100 kilojoules or kilocalories, whatever we get. So now if we are supplying 500 kilojoules to the system, what is possible is that you will have part of the elements or part of the atoms which are there in the ground state. Maybe 2 of them will go to level 1, 1 will go to level 3, and you will have 2 more in level 4. So you get a mixture. Basically, what atomic absorption does is it gives you light of a specific wavelength, which is comparable to the transition from the ground state to the first excited state. So we can always use higher energy, but the problem with higher energy is you get more number of excitations. So obviously you will get more number of emissions. So that makes things a bit complicated at times. Now we all know that the intensity of these lines will be, I would say, proportional to the number of which are there, number of excited state electrons, and number of excited atoms. So the probability of the transition determines what the intensity of the lines. Now, it often happens when we are doing these kind of spectra, we are recording a spectra, and there is a sudden drop in the spectrum. So why does that happen? That happens because of self-absorption. Now, what is self-absorption? Self-absorption is nothing but, say, suppose a particle which is in level 1, it is coming down to level 0, and in the process it is giving out a finite amount of energy. Now, this finite amount of energy is not emitted in the form of light, but this is absorbed by a particle which is there in the ground state, which we say as the cool gaseous atoms, and it gets promoted to the first excited state. The reason I'm talking a bit in detail is because I was given to understand that we have a large number of students who are listening to this presentation. So just to make things very clear for them, I'm really, these are very, I would say, normal things for teachers, but keeping the students in mind, I'm a bit elaborating on one or two topics. And you have the high energy sources. So when we are talking about atomic absorption, we will always be using high energy sources. Now, using high energy sources has its advantages, which we utilize for atomic absorption spectroscopy, and it has its disadvantages also. The major disadvantage is often if we supply energy which is much more than what is required, a process of ionization takes place. So what happens is, now you have a metal, you have something which is X. This becomes X plus. The spectra which X plus gives out will not be identical to the spectra which we observe for X. So we might get confused, what do I really have? And the problem area is, say, you have the periodic table is, say, in such a way that you have X, Y, and Z. Simultaneously, 3 elements are there in the periodic table, and we are using Y plus. The spectra of Y plus would be exactly similar to the spectra of X. So there we get confused. Do I have X or do I have Y in the sample? Because now Y has become Y plus, and spectra of Y now is similar to what the spectra of X is. So this problem we often observe when we are dealing with ionization of using high energy sources. Now, coming to non-flame techniques, non-flame atomization techniques. So by the word non-flame, you can well understand that will not be using flames right here. So what we use here? We are using, in one case, we are using a DC source, and in the other case, we are using an AC. This is known as a low voltage DC arc, and this one is known as a high voltage AC spark. Now, I just go one by one. So the DC low voltage DC arc system of the design is something like this. You have an ammeter which will record the DC current which is flowing in the circuit. You have a resonance control the current, and you have an inductance L. The role of the inductance is basically to have a current source which will give you an uniform flow of current through the circuit. Do not use this inductance. What happens is you get an irregular flow inside the circuit. So we do not want that. That is the reason why this inductance is there. So the advantages or the characteristics of a low voltage DC arc is it is highly sensitive. It can detect very small concentration. So it is often used to identify elements, whether they are there or not. Since even if the element is present in a very small amount, we can very easily identify whether the element is there or not. But the problem is, results are often non-reproducible. So you have an element in your first run, maybe in the second run you don't find that element. Something happens where there is the reason behind this that you need a large sample material. When you are taking a large sample material, and you need to completely burn the sample. So basically all of these methods would be requiring the complete burning of the sample prior to estimation. So when you're burning a sample completely, it often happens is you get an average value. So for maybe for the first run, average value which you got your element A. But when you're doing a second run, the average is somewhat skewed and you don't get A. Instead, so for the second run you find, so first case you had A, and in the second case you do not have A. So this is a major problem with the low voltage DCR. Now we shift to the AC, high voltage AC spark. Now the role of the transformer is basically to charge enough amount of charge in this capacitor, and once enough charge is stored in this capacitor, it generates a spark between these two arcs which are there in the diagram. Now, The advantage of this is you can really work with very small materials. Here you need a large amount for the left-hand side diagram, whereas in this case you need very small materials. And another advantage is you can really work with low melting point materials. That is, materials which are very volatile. In the first case, what happens is, since you're getting an average concept, molecules or systems which are more volatile atoms, they would basically just, if I put it out from the system, you won't be able to identify it. But for low melting point materials, the AC SPARC method is better, but it has its share of disadvantages also. The sensitivity is relatively low, although it's much more reproducible than the DC SPARC. So these are two methods by which you can carry out these non-flame atomization techniques. You can really have pages and pages around this. I'm not going into those details, just giving you a brief idea how we can atomize using non-flame technique. Now, these non-flame techniques have always been used, and this is a list which is taken from Vogel, where you can really clearly see that you can detect samples from 1% to 10 to the power minus 4%. This is really low detection levels, 10 to the power minus 3 to 10 to the power minus 4. So now these are a list of elements where you can always very clearly see, for the first row of elements, you need a very higher detection level, whereas for the last row of elements, these can be detected at a very much more lower level. Now, a typical spectra would look like this, where you have almost all the elements which could be detected. This is around 60 elements which can be detected, 55 elements, which can be detected using these kind of arc techniques. And there is a basic method which is used for detecting elements using this arc technique, which is known as the RU powder method. That is a Ray's Alchemist powder method. Now, what is the principle of this method? The principle of this method is, say, suppose you have 5 different elements in your sample. Now, these 5 different elements are in different proportion. And obviously, we all know that when things are in a higher proportion, we get multiple. Now we go on increasing the concentration of these samples, these elements which are there in the sample. So we go on decreasing the concentration to such a level that even there are some lines which will always remain. That is, maybe we are taking a concentration which is very, very low. So these are lines which will always remain in the spectrum. These are lines which we see as the most sensitive lines. This is something similar to what we see as a fingerprint region in other spectra methods that we have understood. So we go on decreasing the concentration level to such a level that we have these lines, and these RU method is a method which helps us to identify the elements which are present in a particular sample. Next is we come to atoms in flame. So that is basically our primary focus area. Now, what exactly happens when we take an atom in flame? First thing I said, we need to atomize the thing. So the first thing we do is we take a solution of the sample and we nebulize. Now, what do we really do when we nebulize? We aspirate the sample into the burner chamber. What is the process of aspiration? The process of aspiration is nothing but creating small droplets of the sample. Now, once these small droplets of the sample has been created, these droplets mixes with the fuel and the oxidant gases which are there. Now, we'll come to this later. So basically, we have two components. We have a fuel and we have an oxidant gas, which helps in the burning process. Now, obviously, there is a complete mixture at times, there is an incomplete mixture at times, and then the entire thing goes to the flame. Now, once it goes to the flame, so you basically go on increasing the temperature. So you have a mist, it gets converted to solid, gas, so you have tiny solids, more heat, liquefaction, and then ultimately you have a vaporization. Now, once we reach here, that is in the vapor form, this is still of no use to us, because the annihilate, these kind of systems which we are studying, these are called as annihilate. It is nothing but, this is the metal of interest, that is the metal which we want to study, is still bound up with some anion. So the metal which we want to study is M. So M is still bound with X. So this is of no use to us as far as atomic absorption is concerned. So we supply more heat to the sample, it gets dissociated into M gas and X gas. Now, this is where the entire process begins. This is where the absorption begins. This is where the spectroscopy begins. Now, there are a few options which will happen here. Number one is, let us look at this particular thermal excitation. So we are continuously giving energy to the system. It is very much possible that since we are supplying energy to the system, some of the gas molecules will absorb this energy and be converted to the excited state. So now this becomes M star. This was M gas, which was in the ground state, and now this becomes M star, which is in the excited state. So this process is known as thermal excitation. Now, once you have M star in the excited state, this M star will obviously come down to the ground state, liberating some amount of energy. And if this is in the form of light, this is the form of light energy, we say this as a flame emission. On the other hand, you have M gas, which is there in the ground state. Now we supply energy. This energy is not taken from energy which is there in the system. And this is the area which is of most importance to us. Now, at absorption of radiant energy, H mu. Now, this H mu has to be exactly similar to the energy difference between M and M star. So, this amount of energy that we are supplying to M out over here, it has to be a perfect match with the energy gap between the ground state and the excited state. And this process is known as absorption. So this is where the absorption is taking place. The absorption is taking place at the atomic level, and hence this particular absorption will be known as atomic absorption. So suppose you have 5 molecules of 5 photons of energy. So 5 M gas would be transferred to 5 M star gas. So we can exactly calculate the number of M gas that we have transferred to the upper excited state. And once it goes to the upper excited state, it can again emit light by a process of fluorescence and come down to the ground. Now, this is where the basic definition is there. So the first one, what we said, this is the flame emission spectroscopy. This is flame photometry. The old name was flame photometry. This is your atomic absorption spectroscopy, and this is your atomic fluorescence. So this is the fundamental, I would say, the flow chart of atomic absorption and an atomic emission. Now, what happens to the population level between the different levels, the population density of the different levels? Now, these are some of the, we said we use oxidant and fuel. Now, these are some of the oxidant-fuel combinations which we use. You can very well see that as we are going down this table, the combustion temperature increases 1850 to almost 2800. And this is the basic Boltzmann distribution law, which we have all This is basically a part of us for chemists and the energy difference between. Now, just if we refer to the previous slide, we had two processes. One was atomic absorption and the other was flame emission spectroscopy. So for flame emission spectroscopy, we need more number of atoms in the excited state. For atomic absorption, we need more number of atoms in the ground state. So there lies the catch. Now, how do we increase the number of atoms in the excited state? Very easy, we increase the temperature and the number of atoms in the upper excited state will increase, or we decrease the energy difference between the two levels, the number of atoms in the upper excited state will increase. Now, the problem is, if the number of atoms in the upper excited state increases, the probability of atomic absorption also increases. So, keeping that in mind, so these are two areas where we can play with. So, playing with the combustion temperature, we can control whether we want an emission process or we want an absorption process, and we can really not change the delta E value because this is fixed for a particular element. So, the only option where we can really play with is we can play with the temperature. Now, this is again a data taken from Google, where you can see for sodium at 2000 Kelvin, the ratio is 10 to the power minus 6, and at 4000 Kelvin, the ratio is 10 to the power minus 3. Obviously, if we increase the temperature, we can increase the number of atoms in the upper excited state. So this will give us a better fluorescence atomic emission spectroscopy. But if we want a better atomic absorption spectroscopy, we work at a lower temperature. So this is the temperature factor where we really balance what we want, the atomic absorption or the flame emission spectroscopy. This is a basic schematic diagram. For an emission, you have a simple, you do it to a flame, and then you have a detector which gives you the emission process. I'll come to detail all of these. For an absorption, now for the absorption to take place, this you see there is an additional attachment. This is the lamp. Now, here the lamp was not there. What is the function of the lamp? The function of the lamp is to give you that particular energy which will transfer M from the ground state to the upper excited state. So basically, the entire absorption process is dependent on this lamp. This lamp will play a major role in atomic absorption. And obviously, when we are doing an atomic fluorescence spectroscopy, we all know, since we are studying fluorescence, this emission cannot be in the same line. It has to be in a different line so that it does not interfere with the emission. So this is fundamental spectroscopic techniques which we use. And this atomic absorption follows Beer's law. If we see absorption versus concentration law, up to a particular region. So we almost get a linear relationship for a reasonable amount of concentration, beyond which there is a deviation for the linearity. As long as we are working in the linear region, we can quantitatively estimate the number of atoms which are being absorbed. This is the criteria, or this is the I would say the principle which is exploited in atomic absorption spectrum. Now let us come to the diagram of a spectrometer. The single beam spectrometer. This is a source, just as I told you earlier. This is the sample cell, is where we have taken the sample. This is the flame and the sample cell together. The monochromator, the detector, the electronic part which converts a detector into signals, and this is the computer monitor where you get the data, or the plotter where the data is plotted to you directly. Now we have one function out over here. All of these I will be coming in detail. So basically, if we look at the salient feature, the light source emits a spectrum specific to the element. Now this is a very important criteria for atomic absorption. That is, this light source has to emit a spectrum for the element which you have taken in the spectrum cell. So if you have sodium out over here, this source must emit a spectrum which is specific for sodium. If you have sodium and you have calcium being emitted out over here, you will not have any atomic absorption. This is one condition, or this is one criteria which must be satisfied when we are studying atomic absorption. When we were doing UV, when we did FTIR, all these different techniques, we used a fixed light source where we studied all our samples. But when we are coming to atomic absorption, this is something which we have always keep in mind, that the source must be identical to the sample which we want to study. So this is a primary, I would say, a precondition which we always have to follow. Now, the light source is electronically modulated or mechanically chopped. So the role of the chopper is basically to control the light and to pass it once to the sample. And then again, when you're looking at a double beam spectrophotometer, once to the sample, which is the reference beam. One, it will go to the sample and then again to the reference beam. Obviously, the role of the monochromator is eventually to give out a single wavelength. The electrical circuit will give you the intensity depending on the number of, I would say, the population of the number of atoms which have absorbed this particular radiation, and so forth and so on. So we'll come into this. Now, what is the primary difference between these? For the first one, you need a warm-up time, whereas in the second one, you can work instantly. Why the reason is because when you're working with the second one, say you just switched on the light now. So right now, once the light will go to the sample, and the next moment the light will go to the reference. And this almost happens instantaneously. The switching becomes instantaneous. So since the switching becomes instantaneous, at any moment, the data which you are getting is normal, which we have always done. The sample minus the reference frame is your data. But when you're doing a single beam spectrophotometer, now since you have to pass it through once the sample cell, and then you remove the sample cell and you insert your reference system out over here. So obviously this instantaneous modulation of light cannot take place. So we have to wait for the light such that the light warms up and gives you a stable emission for which you can study. So this is something which we always do when we are doing a UV visible spectrophotometer with a single beam. We switch on the spectrophotometer, we wait for about 10-15 minutes for the UV light to stabilize, and then we carry out the experiment. Now, these are all, I would say, computer controlled these days. The chopper is replaced by compensated systems where they automatically move and it passes the light once to the sample cell and then again to the reference. So these are things which are now very standard, just like any other spectrophotometer. I started off with a very primitive design of a spectrophotometer, and this would be a more modern design of an atomic absorption spectrophotometer. Now, what exactly is, we were talking about the light source. So this is very important as far as atomic absorption is concerned. So what exactly is a light source? There are primarily two types of light source, which we are going to talk about today. One is the hollow cathode lamp, and the other one is an electrode-based discharge lamp. Now, what exactly is a hollow cathode? Now, this is nothing but an evacuated cylinder where you have a cathode which is in the shape of an U, and this cathode is hollowed out cylinder of the metal whose spectrum is to be produced. Now, I told you earlier, this metal has to be same as the metal whose atomic absorption we want to study. So this is, say this is metal X. We're doing with X. We can only study the atomic absorption of X. The anode is tungsten, And the entire thing is sealed in a glass cylinder, which is filled with either neon or argon. And there's a quartz window out over here through which the emission can come out from this particular hollow cathode. Now, see, there are two choice of atoms, two choice of gases which you can consider. One is neon and one is argon. Now, it is a choice of using a metal combination and a gas. So basically, all metals will not work with neon, or all metal will not work with argon. So depending on the metal which you want to study, choose whether the gas would be neon or the gas would be argon. If you are choosing working with a neon gas, the glow inside would be reddish in color. If you are working with an argon gas, the glow inside would be blue in color. And you have 60 different hollow cathode lamps for 60 different elements which you want to study using atomic absorption. So one atomic absorption, each element will have a different hollow cathode lamp. So right now, the literature which I could find was that we have 60 different hollow cathode lamps which are available. Now, how exactly does the hollow cathode lamp function? This is very interesting. That is, you have the hollow cathode lamp, which is inside an evacuated cylinder, I would say, filled up with either argon and neon, whatever. Once you have this, and you apply charge to this, they have a large voltage. So what will happen? Immediately, there would be an ionization of the inert gas which is there inside that particular cylinder, that hollow cathode. The entire thing. এবার শোনা যাচ্ছে? গলা ব্যথা হয়ে যাচ্ছে। শোনা যাচ্ছে সঞ্জীব দা? বলি না শোনা যাচ্ছে?
মুকুটদা শোনা যাচ্ছে, মুকুটদা শোনা যাচ্ছে।
ঠিক আছে, ঠিক আছে। Thank you, thank you. So you have a large voltage. The moment you apply a very large voltage, there is an instant ionization of the inert gas. So once the gas is ionized, it becomes Ar+. Now this gas goes and hits the cathode. The moment it hits the cathode, it transfers the energy and it emits a metal off from this cathode. So this was M, the metal which we had used to build the cathode. So one M is emitted, which is in the ground state. This process is known as sputtering of atoms. So the inert gas goes and hits the cathode, and you have the atoms are sputtered from the cathode. So this is the first step which happens. Now, once this is still in the ground state, this is M0. Now you have other argon, ionized argon, which is there in the system. So say another argon, ionized argon ion, transfers its energy to M0, transferring it or lifting it up to the first excited state, that is M star. In the process, it loses its energy, but it transfers the energy and takes M from the ground state to the first excited state. So the atoms get excited by collision. Once this happens, so you have an M star. Now this M star emits a particular wavelength, which is nothing but the energy difference between the first excited state and the ground state, and it comes down to the ground state. So M star to M0 and lambda is emitted. So atoms decay to the ground state, giving out a specific amount of energy. Now this lambda, which is emitted, now this goes through the sample cell. Now once it goes through the sample cell, now this sample cell, now suppose M was sodium. Now this sample cell contains sodium which is in the ground state. We had seen in that schematic diagram. Now this sodium now absorbs this lambda and gets transferred to the excited state. So you have an atomic absorption of a sodium atom, and there's transfer of sodium from the ground state to the excited state. This is the process of atomic absorption. So basically, what is very important, which we have to always keep in mind, that this wavelength of the emitted, I would say the emitted wavelength from the hollow cathode lamp should be identical to the energy difference of the element which you want to go for atomic absorption. This is a primary condition. So for this reason, you need 60 different elements, 60 different hollow cathode lamps for the different elements which you want to study. So this is the primary condition, and the advantage is this is an excellent, bright, stable line source for most of the elements. So hollow cathode lamp is extensively used in atomic absorption. Now, what are the characteristics? It both includes advantages as well as, I would say, the limitations. I won't say disadvantages. It obviously has a finite lifetime. Now, why does it have a finite lifetime? It has a finite lifetime because the amount of the gas which is there, as we are going on applying a high voltage, there is a continuous ionization of the gases. So there would be a time when there would be no longer gases to ionize, and so the hollow cathode lamp will not function. Often manufacturers go for a large volume, that you can have a large volume of gas, and it will obviously give you a higher finite lifetime. So this is one problem with hollow cathode lamps, that is the lifetime is quite finite in case of hollow cathode lamp. And when you have a sputtering, if you are looking at volatile metals, often happens that after sputtering, the N0, which is emitted from the hollow cathode, is no longer in the vicinity for transfer of energy. It goes far away from the cathode. So those are processes where you have a loss of energy. So this has come out from the cathode, but it really does not give us a lambda which is of interest to us. And there is another problem. We often have hydrogen being evolved during all these processes, and it goes and sticks to the anode. So the anode was, it happens that after a finite time, there's a coating of hydrogen on the anode, and the functioning gets disturbed. So nowadays, we are using tantalum, which is another element on the anode, and it is known as a Detter element. That is, whenever a hydrogen is emitted from the cathode, it is very easily absorbed by tantalum. Obviously, the advantage is you need a very pure material to have a single emission. If you have a mixture of elements which you want to study simultaneously, you need a multi-element cathode. That is a cathode which will give you all types of emissions. Now, obviously, an alloy would be a suitable candidate for that. But there is a disadvantage with multi-element cathodes, is you have a loss of intensity. These are not as intense or as specific as a single emission cathode lamp. So what is normally used is you have a multi-cathode holder setup. That is, you have at least 4 to 6 cathode lamps which are fixed, different element cathode lamps, so you can really simultaneously read 6 absorptions. And obviously, this emission would be current dependent. So we need to control the current between the cathode and the anode for a proper emission. And obviously, these are now again controlled electronically. These are modulated electronically. These are really not a problem anymore. And this is how a hollow cathode lamp looks like. This is taken from the net. Now, you have an electrodeless discharge lamp. Now, when do we use an electrodeless discharge? This is used when you have volatile elements. See, we studied that when we have volatile elements, it goes far away from the cathode, and it really does not help. You have low intensity elements, that is where really the light coming out from the cathode is not good, and obviously lifetime is a major issue for cathode lamps. So to address that problem, we have electrodeless discharge lamps. The basic structure of an electrodeless discharge lamp is you have a lamp out over here which is sealed inside a quartz bulb, and this lamp is made of the metal or the salt which we want to study. So here again we are using a specific metal or a specific salt whose atomic absorption we want to study. There it was the cathode, here it is the lamp. And the entire, there we generated the current by a cathode and the anode. Here it is generated by an RF generator, which is known as a triode. So when we are applying power, an RF field is created. So this will obviously vaporize, excite the atoms, and it will cause them to emit a characteristic spectrum. So the functioning of the cathode lamp and this electrodeless discharge lamp is more or less similar. That is, each of these gives out light of a particular wavelength. Now, obviously, EDL is much more intense, and in few cases, it is more sensitive. Though the lamp of choice, I will always say, is the HCl, the hollow cathode lamp. It has better precision and lower detection limits, but the major advantage of an electrodeless discharge lamp is the typically high lifetime which we find with these kinds of. So what we have done, we have emitted a particular wavelength of light which the metal must absorb. So for that to happen, now we come to an atomization, which is a flame technique. So what is a flame technique? We insert the sample out over here. This is the sample capillary. This is known as a pre-mix burner system. That is, we are mixing everything before we are putting it into the burner system. That is why it is known as a pre-mix burner system. So we inject the sample from here and we introduce fuel oxidant from other inlets. So once it goes into this blue part, the sample is there, the aspirated sample is there, the fuel is there, the oxidant is there, and all of them mix together. Now, the advantage, or I would say the functioning of the blue part is this ensures a complete mixing of these three components. Now, once this is completely mixed, I'm not going into the details of this burner system. Once it is completely mixed, this goes to the burner head. This is where the combustion will take place. So this is where the basic thing is taking place. So the entire mixing takes place here, and then if anything is wasted and all those things, you have these attachments where it is, you can bring it out from the system. So after a complete proper mixing, it goes to the burner head. Once it goes to the burner head, the process of burning takes place. Now, what are the advantages of this kind of thing? So once it reaches there, it gets converted completely to the gas, that M0 which is there, and during this process, M0 gas, which we saw in the diagram. Now this M0 gas is produced here. Once this M0 gas is produced here, we have the wavelength coming out from the hollow cathode lamp. This will pass through this particular system. Once it passes through this particular system, this M0 gas will absorb that lambda and go to M star gas. So the atomic absorption process is taking place within this burner system. So if you remember the diagram which we saw, we had a sample system where I said the sample absorption as well as the atomization process is taking place. Now, what is the advantage of these kind of pre-mix burner systems? You have a very stable flow because you are completely mixing everything before you are introducing it to the burner head. It is non-turbulent. It is almost a very smooth flow. This is noiseless. So non-turbulent means there is no background noise. There is no. There are absolutely no nothing which is disturbing your system. So another advantage is you have a big fuel from here and you have a mixing the oxidant from here. we all know that the fuel and the oxygen are both very combustible. If you are bringing them separately into your mixing chamber, there are less chances of explosion during in the pipeline. So this is considered a very safe technique for carrying out such kind of mixing process. And a major advantage is you can turn this head 90 degrees. You remember that when we were doing say any kind of absorption in maybe in UV visible spectrophotometer. So if the surface, if the concentration is large, when we are passing through the entire head, we get an absorbance which is more than 4. So we really do not get any peak. Instead of using a 1 centimeter cuvette, we used to use a 1 millimeter cuvette. So automatically we bring down the absorbance 10 times. So this is something similar. We can rotate this from here to a direction here. So this length, say this length was X. Now once we rotate it there, absolutely 90 degrees, this length will now become maybe X by 2 or X by 3. So just by turning the head, we can control extra, or we can control samples which have a very high concentration. It has a major disadvantage. Only 5% reaches the burner head. That is, all this mixing and all these things takes place here. So eventually, whatever you are doing, only 5% reaches here. So there is a major loss of sample system which takes place. And if you are dealing with mixed solvents where you have a more volatile solvent, obviously the more volatile component will go, the other components will not be going into you. So this is a major problem with mixed burner systems. Next, we come to a total consumption burner. Now, this is an anilate solution. Here, there is no mixing which is taking place. So you have a capillary which picks up anilate to the tip. This is the capillary tip. You have a fuel injector, you have an oxygen, and entire mixing is taking place here, and you have an instantaneous burn. Obviously, the moment you do this, it has its share of advantages. The major advantage is you have an entire consumption, entire combustion. So whatever you are going into the system, the entire thing goes into combustion. But this is a very non-uniform flame, and this shows heavy turbulence. Because you know, these flow rates, if there is a slight change in these flow rates, the burning will get affected. So everything has its plus and a minus. So for a total consumption burner, you have an entire consumption, entire combustion, but you have a very non-uniform flame, and often background turbulences really affect the data that we have.
Motion energy,
Now, coming to non-flame techniques, this is an area which is often incorporated in atomic absorption spectrophotometers these days. This is known as an electrothermal atomization. Basically, this is a thermal atomization by the application of an electric field. What exactly? I'll just give you a very brief idea of it. We have a graphite jacket here. This graphite jacket is along the light path. So this graphite jacket has a dual role. It acts both as a sample cell and it is used as a heating component. And this is connected through the outside. You have two chambers. These are filled up with argon. And the connections come from here. We inject the sample. This is a septum type of a thing. We inject the sample from here. There is a small gap here. So you take a big syringe, you put it directly into the graphite tube, and the sample directly comes out over here. Now, what is the advantage? What is the advantage of this? The advantage is we were dealing with only solutions when we are in the previous case. Here, you can use a slurry or you can even use a solid sample. And temperatures are slightly higher. There it was around 2600, so this is 3000 degrees centigrade over here. Now, this is known as a graphite tube furnace. Often these days, you have atomic absorption spectroscopies where you have a graphite furnace as well you have a flame furnace. So these are known as GFAAS, so graphite furnace atomic absorption spectroscopy, or graphite flame atomic absorption spectroscopy. So these days, both of these are combined in often many of the spectrophotometers. And a very simple method is, instead of such a huge setup, we at times get use of graphite rod atomizers. That is, the entire atomization process is taking place on a single rod. The basic functioning remains the same. That is again a type of an electrothermal atomization which is taking place there. But the problem area is cleaning this. The sample contamination is a major source for graphite furnace. Now, coming to plasma. Plasma is now basically one of the materials of choice. And this word was, I would say, coined by Langmuir in 1920. So this is a pretty old, almost 100 years, almost exactly 100 years. So what exactly is a plasma? A plasma is a gas of ions, atoms which have some of their orbital electrons removed, and you have a large number of free electrons which are there in the system. Obviously, when you have an ionization, something like this, we are producing very high temperature. Because of this very high temperature, there is an almost complete ionization which is taking place. Now, if this ionization is taking place, we hardly have any material which is there in the ground state. So, most of the cases when we are dealing with plasma sources, atomic absorption becomes very difficult. That is something plasma is generally considered not used when we want to. But obviously, if you want to do a flame chemical spectroscopy, plasma is the material or the atomization source of choice. Now, again, the gas which is used is argon, and there are two types of plasma techniques. One is a direct current plasma, and this is something which we are all familiar with, at least acronym ICP. One is the inductively coupled plasma. Now, this is a schematic diagram. I'll briefly go with this. You have two anodes here, and you have the cathode block here. So these two anodes are basically argon, and you have a sample which is again taken in argon, and the entire thing is basically mixing. This is a region which is almost equidistant from the anodes and from the cathode. So this particular region is where the maximum generation of, I would say, plasma, or the maximum concentration of charge is. So this is a process where you have a direct coupling plasma, that is, a directly coupling the plasma over here, and the core temperature which is achieved over here is almost 10,000 Kelvin. So at 10,000 Kelvin, you cannot have atoms, you cannot have metals which are in the ground. So it is difficult, or rather it is impossible to do atomic absorption when you're using plasmas. And what is an ICP? An ICP is basically almost similar, but you have a capillary action out over here. This is again where the sample goes into the system, the capillary injecting tube. This is a tangential argon flow which maintains the flow of argon. This is the argon plasma gas inlet. Argon is converted into plasma, and entire mixing in presence of the radio frequency induction coils. The function of these coils is they generate a radio frequency which will generate a very high current and which will eventually burn the samples. Now, this is the advantage of ICP is you can have different temperatures. See, here it is 10,000 Kelvin at the core, but if you're going up, it is 6,000 Kelvin. Why ICP is preferentially used is to play with the temperature with ICP. But we should always keep in mind that these atomization techniques are primarily used for atomic emissions. Now, coming to a monochromator, these are things which we all know. The function of the monochromator is nothing but it takes in all different colors. This is what we normally find in the book, so I thought this would be there. And this becomes more easily understandable. So it takes in all different colors, but it only allows color of a particular wavelength to come out. So after the sample passes through the sample burner, it goes to the monochromator. So the monochromator will only allow that particular wavelength which we want it to study. And this is done by a set of mirrors or lenses both are used. So these mirrors or lenses basically breaks down light into a particular component, and the monochromator gives out light of a particular wavelength. Now, how do you really calibrate? You've done a study. You more or less the basis. This was the basic structure of the atomic absorption spectrophotometer. Now, as we said earlier, there is a linear region. This is the absorption versus concentration of nickel. Pardon me, I could not get the X and the Y axis. I copied these from materials, but somehow the axes were not coming. So the axis should be there. And in all of the cases, the y-axis is absorbance and the x-axis is concentration. So if we are studying a sample which is suppose within the linear region, so we can go ahead with one standard. And we are taking a value, say this is 3. If we want to study a sample concentration sometime within 3, so we draw a sample curve. So this would be linear from 0 to 3. We have a linear calibration curve, and then we find out the absorbance, and we can say, well, the sample contains such an amount of so many. What this is the concentration of the unknown element in the sample. Now, suppose it often happens that you want a concentration somewhere here, which is beyond the linear region. In those cases, we go for a 2-level calibration. And the condition is the second level calibration must be 3 times the concentration of S1. So if S1 is 3, this should be at least 9. So this is a 2-level calibration. You want to go for even more higher concentration, we go for a 3-level calibration. Again, S3 could be 6 times of S1. And once this is complete, we draw a calibration curve and we can find out. So depending on if you want higher concentrations, we go for higher number of standards. If we want lower concentration, we go for lower numbers. Now, basically, I'm almost at the end of what I wanted to tell you today. So there are different types of interferences which we have in our syllabus. There are 2 main interferences which are concentrated on the syllabus. One is the chemical interference and other one is the background absorbance. So what are the other types of interferences? One is an ionization interference. So what exactly, very briefly, an ionization interference is if you have a higher temperature, you have less number of atoms which are there in the ground state. So if you have less number of atoms in the ground state, there is less atomic absorption. And so obviously, we would really not, if our focus area is atomic absorption, we would rather work at a lower temperature. What is matrix interferences? Matrix interferences are if the matrix elements, that is, we have taken a sample and we have taken a standard, if the viscosity, surface tension, burning temperature, these are different between the sample and the standard. So obviously the calibration curve which we draw will not be correct. So such interferences are known as matrix interferences. Emission interferences, just as I was telling you, when we are dealing with high annihilate concentration, this is really not, preferably this should be avoided. We should be working with a low annihilate concentration. Spectral interferences, we have other elements which are absorbing in the region which we are currently studying. So suppose we want to study element A, metal A, and we have metal X, which has a similar or which has a very close absorption maxima. So it often happens that X will interfere in our data of A. These are primarily a very fundamental knowledge of the different interferences which are observed in atomic absorption. Now, coming to chemical interference, since we have it in our syllabus, now what exactly is a chemical interference? Why does it happen? A chemical interference happens. Our primary target of producing atomic absorption is we need atoms which should be in the ground state. So, if we have a thermally stable compound formation or we have an ionization, there would be a feasible issue. We have a ground state where we have a stable atom, gaseous atom. Now, once we have a stable gaseous atom, it will not be totally decomposed. So, if it is not totally decomposed, say I have a concentration C, and it forms an element, it forms some species where I'm not able to dissociate maybe 50% of my ground state atoms. Obviously, I'm dealing with a concentration which automatically becomes C/2. So that is definitely, we have to avoid such kind of thing. And obviously, if ionization happens, though ionization is a different ionization interferences characterized separately, but these two go hand in hand. That is, we often increase the temperature to have a better ionization, a better dissociation, I would say. But these better dissociations are often accompanied by higher ionization. So we have to balance between the dissociation and the ionization. Obviously, if we increase temperature, this stable compound will disintegrate. But the moment we increase temperature, ionization will also increase. We often do add releasing agents. This is my stable compound. We add a releasing agent R. So now R binds with X to form Rx, and M is let free. Or we have a solvent extraction process where we repeatedly extract the metal using solvents, such that when we are incorporating the metal into the system, it is as pure as possible. Now, just coming to two specific examples. Suppose we are estimating calcium. Now, phosphate is a major problem in estimation of calcium. This is the curve of calcium estimation. This should be your theoretical curve. But the moment you add phosphate, the curve takes a shape like this. Now, why? This is interference of calcium in presence of phosphate. And this is a typical example of chemical interference. So, first thing, you increase the temperature. So, you go from an air acetylene flame, you go to a nitrous oxide acetylene flame. You have this compound gets more, it gets dissociated. Now, we add releasing agents like strontium and lanthanum. So these will convert the phosphate into the corresponding strontium phosphate or the lanthanum phosphate. So now once this conversion takes place, calcium is now free. So phosphate no longer interferes with calcium. Calcium goes through the absorption process as its own. And another thing is often done is we knowingly add PGTA into the complex, calcium into the system, into the mixture. Calcium readily complexes with PGTA, and this again gets very easily dissociated. So phosphate, once this calcium EDTA complex happens, phosphate cannot bind to calcium unless done. Another is, again, estimation of molybdenum. Here, calcium is the spoiled brat. So again, we go for a higher temperature, we go for a nitrous oxide acetylene flame, and aluminium is the releasing agent out of it. So these are methods by which we go for such kind of things. Now coming to background absorbance primarily happens due to light scattering. and due to absorption of light by unassociated molecular forms. So in order to get out of our details, I think we're taking almost 1 hour 15 minutes, so I'll brush up slightly. So in order to correct this background absorption, this is an example in zinc estimation. If you have sodium chloride in the sample, it overlaps with zinc. If you have such molecules which are there in the solvent, this will again, due to undissociated molecular forms, this causes background absorption. And this is mainly valid in the UV. And we have two types of methods of background absorption. One is deuterium arc and one is the Zeeman effect. And another thing you should always keep in mind, that background absorption affects electrothermal atomization much more than flame atomic absorption. So if you are talking about flame atomic absorption, you really do not need to think much about background absorption. But if you are doing an electrothermal atomic absorption, you really have to consider the background absorption. Now, this is a deuterium arc. This is nothing but the deuterium source is continuously lit up. So this is known as a continuum source. Now, the two lamps are observed by the detector alternately with time, and an absorbance will only be displayed when the absorbance of the two lamps differ. So you have, this was a normal setup. In addition to the normal setup, continuum source, which is a deuterium arc. So this again continuously emits radiation and the sample, and this goes on continuously. It's flip-flap process continuously happens. Now, why? What is the advantage? The advantage is the background absorption will absorb both sources equally. Now, once it absorbs both sources equally, it is ignored. But the atomic absorption, which absorbs only the primary source. Now, since atomic absorption is wavelength specific, it will not absorb this continuum source. So we can very easily, it will not contribute to the reading. So the reading would look something like this. If you look at a timing diagram, you have both here and then you have only the background. You have both here and then you have only the background. And an automated background correction. This is without the background correction. And once you do the background correction, these lines are no longer there. You only have the line due to the presence of lead in the sample. Another, these are the basic thing you have to keep in mind is I would say the optics is important for continuum source, and it is very important that you have to align the sources properly such that this flipping occurs very nicely. Now, next is you have a Zeeman background correction. It is nothing but Zeeman effect, that is we are splitting up a single level into multiple levels in presence of a magnetic field. So the logic is the central level does not change. There is a level and these are split symmetrically. So you have a central level and you have two asymmetric levels, one lower and upper. So it can be 3, it can be 5, it can be something like that. And when you are doing it in the presence of an electric-magnetic field, you get a single line. But the moment you do it in the presence of a magnetic field, you get a triplet corresponding to 3 transitions, 1, 2, and 3. Now, this single transition and this triplet transition, the advantage is that the single line atomic absorption is split into 2 different, which is symmetrically placed. Now, the spectral nature of the background absorption, which was happening, it is unaffected by the magnetic field. So we can very easily see that we have a line splitting up into 2 different, symmetrically it has 2 other lines with it. So we immediately know, well, this is our line of choice, the others were background effect. And the magnetic field is applied around the atomizer or around the primary source where the radiation is there. So other things which are there in the system are not affected by the magnetic field, and hence it has the spectra has no effect on those Now you have different types of background Zeeman effect. One is the DC Zeeman, one is a transverse AC Zeeman, and you have a longitudinal AC Zeeman. And there is another thing, the last slide, that is you have a few water analysis techniques in our syllabus. Now these are all taken from Manual of PerkinElmer. They have explicitly given what is to be done, what is not to be done, and those manuals are available online. So first is analysis of natural water, where you can find out calcium, copper, lithium, magnesium, manganese, potassium, and all these things. You have fresh water, determination of total chromium. Chromium is chelated and extracted into methyl isobutyl ketone. And you have analysis of natural waters, determination of, here you have a number of metals. Again, all these metals are simultaneously extracted by chelation into methyl isobutyl ketone. So these are given in detail with the PerkinElmer catalog, which is available online. Even I can share it with all of you if you need it. And we can always share it with the students, because these are very specific techniques, and these are generally, normally, I did not find it in any of the books which are there for atomic absorptions. And another thing I would like to say, that these techniques often differ slightly when you're going from one company to another. So a method of PerkinElmer would be slightly different from the method of another company would be slightly different from another. So, but primarily, if we can give a basic concept to the students, I think that should be good enough. And I would really like to acknowledge, because I will be very honest with you, I have never done atomic absorption in my life. So when Shoma told me, it was basically a goal from the blue for me. I tried to gather some information and I shared it with all of you. So the primary sources were Vogel, spectroscopy manuals of PerkinElmer. These are freely available on the net and these are downloadable, and different research publications which deal with atomic absorption and flame emissions. And I think I've been able to give some idea, I don't know how much, because I am never an expert on atomic absorption, and I'll be very honest and very candid with you. This was just an attempt, and I was learning the process along with all of you and trying to give you an idea, very basic idea of what atomic absorption and flame emissions is all about. And finally, thank you all for your kind attention. Thank you so much.
তোমাকে পাঠিয়েছিলাম মিলে আসবে শেষ হয়ে গেছে ঠিক আছে আমি করে দেবো ঠিক আছে
Thank you, Mukku, for your very informative, illuminative, lucid, compact, and covering the whole syllabus within a very short time. Thank you very much. I think it will act as a starter for the both for the teachers and the students of chemistry students, particularly honor students. Thank you again. There are some questions. I'll tell this. What type of Abhishek Sannal asked, what type of burner means? Is it burner or mantle? Is it burner or mantle? What type of burner means? Is mantle or burner?
No. This is an absolutely different system. This is not a mantle. This is a composite burner which is all together. It is not that you can do it in an open flame. It is all within the atomic absorption spectrophotometer. So if you, I'll just go back to the slide. Probably that would be better. And to if that helps, just a second. Just give me a minute, another. So this is what the burner looks like. If you take this is a cross section of the burner. But if you look at the burner for photographs, which is there in the net, this is a small setup. This is the entire thing is within the atomic absorption spectrophotometer. So from outside, you can see nothing. You can only inject the sample from here. That is all that we can see. Nothing more.
হ্যালো
হ্যালো
মুকুট
হ্যাঁ বলুন
হ্যাঁ can I regarding a solid sample only, what to do just to hit the how to vaporize this material by either by using say laser technique or something like that? Is
no,
it so?
solid samples you have to use a graphite furnace. For solid samples, we need the graphite furnace.
For
that is an electrothermal atomization where you need the graphite furnace.
Graphite furnace. Okay.
Graphite. The graphite, either the graphite furnace which I showed you, or the graphite pot furnace is used for solid sample.
Another question from Niloy Korchaudhuri. Is there any probability of lowering the lambda value before absorption of N0?
Lowering the lambda value?
Is there before absorption absorption by
then how can you change the lambda value? The lambda value is
exactly.
The lambda value is specific for that particular element. So that lambda value is the energy difference between the ground state and the excited state. So that is beyond our control.
Exactly. This is God gifted by nature. Actually.
Yeah, that is something. Basically, that is the concept. That is the fundamental principle, which is being used for atomic absorption. Is that each and every element has a specific lambda value. Absolutely, has a characteristic lambda value.
Another question done by again Niloy Korchaudhuri. If the concentration of ground state atoms diminished with time, how we will get a continuous spectra?
We don't get a continuous spectra in atomic absorption.
Yes.
Atomic absorption will never give you a continuous spectra. It is a one-time phenomenon.
Actually, there is no relation between the concentration and continuous spectra. Continuous spectra actually lie in spacing when there is a continuum.
That is in case of emission spectra. But when you are talking about atomic absorption spectroscopy will only give you one shot where you count the number of atoms that you have transferred from the ground state to the excited state, depending on the number of photons which you have been able to emit from your hollow cathode lamp. So this is a single step. You start the hollow cathode lamp, say 10 atoms are emitted, 10 photons are emitted. So 10 atoms would be transferred from the ground state to the excited state.
Another question from Devarati De. What is the unit of concentration in the calibration curve?
This is usually in the range of micrograms per liter.
Okay. That's all.
Excuse me.
That can even go up to milligrams per liter, but normally it is in the range of micrograms.
Okay, there's no other question. Is there any?
বলুন শুনতে পাচ্ছি।
হ্যাঁ বলুন। হ্যালো। হ্যালো।
হ্যাঁ
কে বলছেন?
হ্যালো।
Good.
From YouTube chat window.
Yes. Both from both. I have taken. So there is no question. Now, once again, I must thank Professor Dr. Mukul Chakraborty for his very informative, lucid, and thoughtful speech. Deborina.
Am I audible? Am I audible?
Yes.
Yes.
I now have the honor and privilege to present the vote of thanks. First of all, I express my heartfelt gratitude to our distinguished speaker, Dr. Mukul Chakraborty, who has kindly accepted our invitation and has delivered an insightful lecture on a very important topic in chemistry and the UG CBCS course of REPSU syllabus. Next, I thank our Honorable Principal Sir Dr. Sanjeev Kumar Saha for his inaugural speech and also for being the patron of this webinar. I am also grateful to Honorable Principal Madam Dr. Lona Mukhopadhyay for delivering the welcome address. I also take this opportunity to thank our IQAC coordinator, Dr. Moinak Roy, for sharing his valuable thoughts on our program. I now express my sincerest gratitude to all the members of the technical team, Professor Chinmoy Bishwas and Professor Durjoy Roy, without whose hard work and perseverance, this program would never have been possible. I also thank all the teachers of Chemistry Department of Rishi Bankim Chandra College, Dr. Ratna Dotto, Dr. Gopa Nandi, Dr. Sheikh Hanan Mondol, Dr. Shoma Sen, Dr. Suranjana Porkar for their valuable suggestion at each and every step. Last but not the least, I thank all the participants who have shown interest in our program and have joined us today to make this occasion a success. Thank you all. Stay safe and stay healthy. Have a nice day. I now declare the webinar to be over. There is an announcement to be made regarding the feedback form. All registered participants are requested to fill and submit the feedback form. The link has already been posted in the Google Meet and on YouTube chat box. Thank you. It's over now.